So the derivative exists on the open interval from a to b. Meaning it doesn't have to include the endpoints. Then there exists at least one value c in the interval a to b, such that f prime of c equals f of b minus f of a over b minus a. Okay, so let's see what this is telling us here. So here we've got some interval from a to b. So we can label these points on the graph. X coordinate is a. So if this is the graph of f of x, we could write the y coordinate as f of a. So the point there would be a f of a. And similarly, the x coordinate at this point is b, so the y coordinate would be f of b. So we could write that point as b f of b. So let's take a look at this graph, see if it's continuous on this interval and differentiable. It is continuous. You see there's no holes, vertical asymptotes, there's no break in the function from a to b. And it's also differentiable because we don't have any corners or cusps or vertical tangent lines in that interval. So what this is saying is there has to be some value c that's in between a and b. So c is somewhere between a and b. It's a specific x value. So that the derivative there equals this f of b minus f of a over b minus a. Well, what is this expression here? Well, that looks a little familiar, and it should because that's the slope between these 2 points. And remember, this line is referred to as the secant line. So one way to look at this is the slope of the secant line. And remember the derivative, f prime of c, that gives you the slope of the function, which is also the slope of the tangent line. So what it's guaranteeing, if these first 2 conditions hold true, if the function is continuous and differentiable, is there has to be some c value in between a and b, so somewhere here, where the slope of the tangent line equals the slope of the secant line. So here you can see, looks like that would be about somewhere right about there. If we draw a tangent line there, looks like it runs parallel to the secant line. So remember, the secant line goes between 2 points, slope between 2 points. The tangent line is the slope at just 1 point on the graph. So that would be our values. In this case, there's just one. But it guarantees there's at least one. So sometimes you might have more than one. Now this f of b minus f over b minus a also has another name besides just being the slope of the secant line. It's also referred to as the average rate of change. And the rate of change is another for derivative or slope. So this is the average derivative or average slope on this interval. So if we were to average all these slopes of all the tangent lines on this interval from a to b, it would be the same as the slope of the secant line. That's also the average rate of change. So there has to be one place where the derivative equals the average. Then Rolle's theorem is just a specific case of the mean value theorem. So it still has the first 2 conditions. It's still continuous on the closed interval from a to b, and differentiable on the open interval from a to b. But it has a third condition, which makes it a little bit more specific. And that's that f of a equals f of b. So let's see if that's true. On this interval from a to b, again, this is the point a, f of a, and this is the point b, f of b. So we're basically saying the y coordinates at the endpoints are equal, which they are. In this case, you can see they have equal y values. So because of that, what it guarantees is a little bit more specific than just the mean value theorem. It guarantees there's at least one value c in the interval a to b, so c still is somewhere in between a and b, such that f prime of c, the slope of the tangent line, equals 0. The reason why it has to equal 0 is take a look at, it's really coming from the same formula. If f of a and f of b are the same, and you subtract them, that's always going to give you 0 in the numerator, which makes the whole fraction 0. So there's no need to calculate the average rate of change. If the f of a equals f of b, the average rate of change is going to always be 0. And you can see here, it's easy to tell where the tangent line has a slope of 0 is right there. There has to be at least one place where the tangent line is 0. And that's even more important in some ways than just the mean value theorem, because where the derivative is 0, remember that's where we find our critical numbers, where you can have relative minimums and relative maximums. In this case, you can see there's a relative maximum at that value C. All right, let's take a look at some problems that involve in using these two theorems now. So it says determine if the mean value theorem and or Rolle's theorem applies to the function on a given interval. And then if either applies, find all values of C that are guaranteed by the theorem. So first we want to see if the function is continuous. They both have that first condition, the function has to be continuous on A to B. So you would look for anything that would make it not continuous. And the main two things you look out for here are square roots and denominators. So here we have a square root. So we're looking at the domain of this essentially. In order to avoid imaginary numbers, x minus 1, what's inside the square root, can't be negative. So the way to say that mathematically, it has to be greater than or equal to 0. And when you solve that, you get x is greater than or equal to 1. And then look at our interval. Is our interval greater than or equal to 1? Yes, it is, from 1 to 5. So we can write down the first condition. F is continuous on the interval from 1 to 5. Now, if our interval had been from 0 to 5, then it wouldn't have been continuous from 0 to 5, and then if that was the case, then it wouldn't be continuous, and neither theorem would apply. But it is in this case. All right, now we want to see if the function is differentiable. What the differential means the derivative exists. So you have to take the derivative next. So f prime of x, well, the derivative of 4 is just 0, and x squared of x minus 1, that's the same as x minus 1 to the 1/2. So we can use the power and chain rule on that. It would be 1/2 x minus 1 to the negative 1/2 times the derivative inside. Derivative of x minus 1, though, is just 1. So when you simplify that, you get the derivative f prime of x is 1 over, the 2 stays on the denominator, and if you give it the negative exponent and put it in radical form, that becomes the square root of x minus 1 on the denominator. So now, when we're seeing where it's differentiable, we're really seeing where the derivative is continuous. So we still have that square root of x minus 1, so it's similar to the last one, except now it's on the denominator, and remember you can't divide by 0. So now, it can be negative still inside there, but it also can't equal 0. So x minus 1 just has to be something positive. When you solve that, x has to be greater than 1. And that's actually okay for differentiable on the interval because, remember, for differentiable, even though it's not differentiable right at 1, if we look at our theorem, notice it only has to be differentiable between a and b, so not including the endpoints. As long as it's differentiable everywhere between them, it's fine, which it is. It's differentiable everywhere x is greater than 1. So, here's your a and here's your b. You can say, it's like second condition, f is differentiable on the interval from 1 to 5 with parentheses. So if those two conditions hold true, then those are the only two conditions for the mean value theorem. So then you can abbreviate this as MVT, so you know the mean value theorem applies. Then to see if Rolle's theorem applies, remember the third condition on Rolle's theorem is that f of a equals f of b. So we want to determine if those are equal or not. So here's our a and b, so let's figure those out. So we can find f of 1 and f of 5 and see if those are equal. So if you substitute 1 in the original equation, probably easiest to use the radical form there. 4 plus the square root of 1 minus 1. Square root of 1 minus 1, that's just 0. Square root of 0, 0 plus 4 gives you 4. If you substitute in 5, you get 4 plus the square root of 5 minus 1. Well, 5 minus 1 is 4, square root of 4 is 2, plus 4 gives you 6. So you can see these are not equal. So Rolle's theorem does not apply. So only the mean value theorem applies here. Just if those have been equal, then Rolle's theorem would also apply. And if it's just the mean value theorem that applies, then remember what that guarantees is there has to be some C interval in between A and B, such that f prime C equals f of B minus f of A over B minus A. But in our specific problem, that means that f prime of c has to equal, our a and b are 1 and 5, so f of 5 minus f of 1 over 5 minus 1. So f prime of c, well, c is just a specific x value that we plug in the derivative. So here's our derivative right here. So f prime of c, if we just substitute in the c for x, that'd be 1 over 2 squared of c minus 1. And then we've already calculated f of 5 and f of 1 when we were trying to determine if Rolle's theorem also applies. So we can substitute those values in. F of 5 was 6, minus f of 1 is 4, over 5 minus 1 is 1. And now we have an equation we can use to solve for c. So we have 1 over 2 square root of c minus 1. That's 2 fourths reduces to 1/2. And then probably the easiest way to go from there is to just cross multiply. So 2 square root of c minus 1 times 1 is just 2 square root of c minus 1. And 2 times 1 is 2. And we can divide by 2. Gives you the square root of c minus 1 equals 2 divided by 2 is 1. And get rid of the square root, you can square both sides. So you get c minus 1 equals 1 squared root of 1. Add the 1 gives you c equals 2. And then double check, remember c has to be in the interval between 1 and 5 in this case, and 2 in fact it is. So that's the c value that's guaranteed. In this case there's just 1. Sometimes there could be more than 1 there. But you know there has to be at least 1. Alright, let's take a look at another example here. This one's 1/2 x minus the square root of x plus 3 on the interval from 0 to 4. So here's our a and b here. So we also have a square root on this one. So in order to avoid imaginary numbers, x has to be greater than or equal to 0. So if we look at our interval, that is greater than or equal to 0, 0 to 4. So the first condition holds true. F is continuous on 0 to 4. And then to see if it's differentiable, let's go ahead and take the derivative. F prime of x. Derivative 1/2 x is 1/2. And this again is like x to the 1/2. So it is plus 1/2 x to the negative 1/2. The derivative of 3, a constant is 0. And so if we simplify this, we get f prime of x is 1/2 plus 1 over 2 square root of x. And we look for restrictions on that. Still have a square root. This time it's on the denominator, so it can't equal 0. So x would just have to be something positive, greater than 0. So it's not imaginary and it's not undefined. And look on the interval. So it would be differentiable between 0 and 4, even though it's not differentiable right at 4. Remember, it doesn't have to include the endpoints for the differential like it does with the continuous interval. So we can say the second condition, f is differentiable on interval 0 to 4. So again, at this point, those are the two conditions for the mean value theorem. So we can say that mean value theorem applies. And then to see if Rolle's theorem also applies, plug in our endpoints, a and b, so let's find f of 0 and f of 4. If they're equal or not. If you substitute in 0, you get 1/2 times 0 minus the square root of 0 plus 3. That's just 0 minus 0 plus 3 gives you 3. And if you substitute in 4, you get 1/2 times 4 minus the square root of 4 plus 3. So 1/2 times 4 is 2 minus the square root of 4 is 2. That's 0 plus 3 gives you 3 also. So this time, the y values and their points are equal. And since they're equal, Rolle's theorem applies as well. And if Rolle's theorem applies, in some ways it's a little bit easier because what Rolle's theorem guarantees, remember, it's a little more specific than what the mean value theorem guarantees. It guarantees that f prime of c has to equal 0. Again, if f and f b are equal, like we just figured out, I'll just make this calculation 0 every time. So now we're basically just setting the derivative equal to 0. So we know f prime of c has to equal 0. And if we look at the derivative here, and substitute c into that, for x, so c is just a specific x value. So do 1/2 plus 1 over 2 square root of c equals 0. And then to solve this, whoops, I just realized I made a mistake here. This was a minus here, not a plus. Sorry about that. So these should be minus signs, not plus signs. Change that. Minus, minus, and minus. There we go. All right, so now, when you solve that for c, if you just add this 1 over 2 square root of c to the other side, then you can cross multiply here. The 2 square root of c times 1 equals 2 times 1, 2. Then divide by 2. And the square root of c equals 1. And then square both sides. So c would equal 1. Let's check, is 1 between 0 and 4? Yes, it is. So that is the c value that's guaranteed by Rolle's theorem. Notice since Rolle's theorem applied, we didn't use what the mean value theorem guarantees because Rolle's theorem is more specific. If we did, we'd get the same answer. Just it's not necessary to calculate f of b minus f of a over b minus a, because we already know it equals 0 since Rolle's theorem applies. All right, let's take a look at the next one here. So this one, if we switch it to radical form, it's probably easier to tell. F of x equals 2 the 5th root of x cubed. And for odd roots, there's no restriction. We're going to have positive or negative numbers, so this would be continuous on -1 to 4. It's continuous everywhere. There's no restriction. Sometimes there's no restrictions at all. In which case it's continuous everywhere, including your interval here. So f, first condition f, is continuous on the interval from -1 to 4. And now let's take the derivative, see if it's differentiable. So probably easiest to use the fractional exponent form. We're using the power rule. 3/5 times 2 is 6/5 x. So that if you subtract 1 from that, subtract 5/5, that's -2/5. And then if you simplify that, you get 6 over 5. And then in radical form, that would be the 5th root of x squared. Negative brings us to the denominator. So we still have an odd root. So in some ways, there's no restrictions, except now it's on the denominator. If this is on the denominator, you can't divide by 0, so x cannot equal 0. So it's not differentiable at 0, and on this interval, that's actually a problem because 0 is in the interval. It's not one of the endpoints. If the interval had been from 0 to 4, that would actually be okay, and it would be differentiable between 0 and 4. But it has to be here differentiable between -1 and 4, and over between it and 0, it's not. So the second condition does not hold true. So condition 2 here, f is not differentiable on interval from -1 to 4. And since it's not differentiable between -1 and 4, that's the second condition of both theorems, so we know neither theorem applies. And since neither theorem applies, there's no c value that's guaranteed. All right, now the next one, let's see what's continuous, but notice that we have a denominator, and remember denominators cannot equal 0, as we have to find. So when you solve that, you get x does not equal 2. X was 2, you get divided by 0, and let's look at our interval. 2 is in that interval, so it's not continuous between -2 and 3. If 2 wasn't in the interval, it would be a problem, but here it is. So because of that, we can say f is not continuous on the interval from -2 to 3. And that's the first condition for both theorems. So again, this is not continuous, neither theorem applies. So if it's not continuous on the closed interval or not differentiable on open interval, then neither theorem applies, and again, there's no c value to solve. All right, now let's take a look at some problems then we're given a table of data here. It says g of x is a differentiable function and has the values given in the table below. And part A says, must there exist a value x equals c on the interval 10 to 20 such that g prime of c equals 0. So on these problems, if you're looking for where the derivative equals 0, then you're trying to see if Rolle's theorem applies. Okay. Or not. Rolle's theorem, let's see if it applies right. So let's see if it's continuous and differentiable. Well, notice it tells you the function is differentiable. And if it's differentiable, it also must be continuous. If it wasn't continuous, it wouldn't be differentiable either. So those are the first two conditions of Rolle's theorem. Remember, Rolle's theorem has that third condition that endpoints have to be equal. In this case, it would be g of 10 and g of 20. But if you look, g of 10 is 23, g of 20 is 21. So initially, I might look like, oh, we can't apply Rolle's theorem. But remember, we don't just have those two, we actually have a bunch of other points as well. So we want to look everywhere in the interval 10 to 20. And let's see if we can find anywhere where the y-coordinates are equal. And if you look carefully, you can see at 10, the y-coordinate is 23, and as well at 18, also 23. So you can apply Rolle's theorem on the interval from 10 to 18, which is within 10 to 20. So it says, must there exist a value? So it's a yes or no question, so your answer would be yes. And then since, your justification would be since g of 10 equals g of 18, and then can reference by Rolle's theorem. And then part B says, must there exist a value x equals c in the interval 10 to 14 says that g prime of c equals 0. So again, we're trying to see if we can apply Rolle's theorem. So now we're just looking between 10 and 14. But if you look between 10 and 14, there are no y values that are equal. So here we can't apply it, so your answer would be no. Your justification would be since there are no known values A and B in the interval from 10 to 14 such that g of A equals 2. That's what we're looking for. In this case, there weren't any places. We should always say no known values. There might be some place in between here where the y values actually are equal, but we can't see it. These are the only ones we know on these 3 points. Alright, so let's take a look at one that's kind of similar, except there's one key difference here. It still says, in this case, v of t is a differentiable function. Since it's differentiable, also must be continuous. Otherwise it wouldn't be differentiable. Next says, must there exist a value t equals c in the interval 20 to 44, such that b prime of c equals 1/3. Notice here it's not 0. So if the derivative, if you're looking where the derivative is not some other number other than 0, then you're trying to see the mean value term can that be applied here or not. So let's look on the interval 20 to 44 right here. And we already know it's continuous and differentiable, so we can apply the mean value theorem. There's no two conditions. The only question is 1/3 the value it guarantees? Remember what the mean value theorem guarantees is that the derivative has to be figure A and B. In this case, v of 44 minus v of 20 over 44 minus 20. So we're going to calculate that and actually see if that's 1/3 or not. So v of 44 is 18. v of 20, using the table, is 8. Over 44 minus 20 is 24. 18 minus 8 gives you 10. Over 24 reduces to be 5/12, which is not 1/3. So if this was 5/12, then your answer would be yes. It does have to equal 5/12, but it's not, it's 1/3. So your answer here would be no. since this v of 44 minus v of 20 over 44 minus 20 does not equal 5 volts. Sorry, does not equal 1/3. Now let's look at another interval from 44 to 80. From 44 to 80 right there. Let's start just a value t equals c in the interval of 44 to 80, such that b prime c equals negative 1/6. So again, since it's not considered as 0, we're looking to see the mean that applies. So let's calculate the same thing, except now we have a different interval. So v of 80 minus v of 44 over 80 minus 44. So v of 80 is 12 minus v of 44 is 18 over 80 minus 44 is 36. 12 minus 18 gives you negative 6 over 36, reduces to be negative 1/6. So here, that is what it equals. So here your answer would be yes. And your justification would be kind of similar to this one, except it would be since v of 80 minus v of 44 over 80 minus 44 equals negative 1/6. And your justification would just have to add, since you used it here, by the mean value, which you can abbreviate as MVT. All right, now let's take a look at multiple choice question here. It says the function f is differentiable on the interval negative 3 to 1. So that means it's also continuous. And f of 3 equals f of 1. F of negative 3 equals f of 1 equals 2. Which of the following statements must be true? Okay. So let's take a look at each of these here. So they all look kind of similar, except notice this first one, it says that there's at least one c where c is between negative 3 and 1, such that f of c equals 0. Notice not the derivative here. So if it's not the derivative, what we're trying to apply here is the intermediate value theorem, the IVT. And on this one, since the derivative equals 0, then we're trying to apply Rolle's theorem. And this one, where the derivative is not 0, it's something else. We're trying to apply the mean value theorem. So for the intermediate value theorem, it's probably easiest if you just sketch a graph of this. This gives you actually 2 points on the graph. When you plug in negative 3, you get 2. And when you plug in 1, you'll also get 2. So let's do a little sketch of our graph here. So over here at negative 3, it's 2, and at 1, it's 2. So those are the points we know there. And this is saying the y value has to equal 0. Well, we know it's continuous and differentiable. If it equals 0, that means it would have to cross or touch the x-axis here. And there's no reason it has to do that. It's continuous and differentiable. It could be up here. It could never touch us. So this one could be true, but not must be. Then let's see if Rolle's theorem applies. Well, if Rolle's theorem applies on the interval from negative 3 to 1, the endpoints, it's continuous and differentiable, which it is, and the endpoints would have to be equal, which they are. They're both equal to 2. So all three conditions for Rolle's theorem applies, so this one must be true. And the last one, the mean value theorem. Well, normally what you do is you calculate and see does f of one, you know it's continuous and differentiable, so it's actually minus f of -3 over 1 minus -3. Does this equal 4 or not? But we can actually calculate that pretty easily because these are 2. That's 2 minus 2 over 4 gives you 0 over 4, which is 0. So, and we knew that already because of Rolle's theorem applied. So this would have to be 4 in order for this to have to be true. So it could have a slope of 4 somewhere. So this is saying does the slope have to equal 4 somewhere? But it doesn't have to. So this one again only could be true. The only one that must be true is Roman numerals. Okay, let's look at one more of these. This one, it says the function is continuous on the interval from -5 to 1. Since it's continuous, that doesn't mean it's differentiable, okay? So it's continuous, it might be differentiable. Well, we don't know for sure. And we're given a couple points, f of -5 is -2, f of 1 is 4. Which of the following statements must be true? Alright, so again, here's the original function of y equal 0. When it's the original function, that's trying to apply the intermediate value there. So the easy way to do that is just sketch the graph again. We've got -5, -2. Point on the graph there, and f of 1 is 4. Remember, the only condition on the intermediate value theorem is the function is continuous, which it tells us it doesn't have to be differentiable. And let's take a look. Does the y value have to equal 0 somewhere on this interval? In this case, you'll notice the graph does have to touch 0 somewhere, has to cross 0, because 0 is in between the endpoints, unlike the last one where it wasn't. So since 0 is in between there, it has to cross not just 0, but -1, 1, 2, 3. It has to hit all of those y values in between -2 and 4 at least once. So this one must be true. Then here, since f prime of c equals 0, we're trying to apply Rolle's theorem. But there's a couple things wrong there. To apply the Rolle's theorem, it has to be differentiable, and we don't know what is differentiable. And we also have to have the endpoints that are equal, which they're not equal. So for those two reasons, only one of the conditions holds true out of the three continuous. This one might be true, the derivative might be 0 somewhere, but not necessarily. So this one only could be true. And finally, the last one has an absolute maximum value on -5 to 1. So the only condition for this, for function to have an absolute maximum and absolute minimum, that's the highest y value in this case, is the function must be continuous. And it does tell it's continuous. So this one must be true. Because even if you don't have a relative maximum, you still would have your endpoints to use. And so it must be true since f is continuous on -5. So in this case, Roman numerals 1 and 3 are the ones that must be true. And that concludes the notes for AP Calculus on the topics of the mean value theorem and Rolle's theorem.